All right, so I don't think this will come as a surprise, but exam 3 is Tuesday. In class, I'll have the sign-up sheet again. Some of you will be in here. Most of you will be in here. Some of you will be in the Orgo labs. What else? So just the little bit of 5 that I did on Tuesday is on the exam, all of 7, most of 9, and really all of 10 that's on there is just that if you do a free radical halogenation, do we have a seat somewhere? Are you on the list? 5, 10, 15. Yeah, so one of you came in late. Who all came in late? Sorry, yeah. No, have a seat. That's the way it works. Sorry. I got told I very much cannot have more than 30 in here, so. Yeah, sorry. Okay, so where was I? Yeah, so all of 10 is free radical halogenation. All right, so if you take Cl2, Br2, light, and an alkane, you can replace, you'll put a Cl or Br on the most stable, the carbon that would make the most stable radical. So most of it's 7 and 9. There's a study guide online. There is a key for the substitution elimination set. So there you go. We'll do the exam on Tuesday. I will turn those back to you on Thursday. I'll email them out to you by Thursday, the end of Thursday. Probably go over some of it in class on Thursday, that Thursday. There won't be any new material after the exam. The final exam, which is Saturday, May 8th at 9 a.m., is going to be equal parts exam 1 material, exam 2 material, exam 3 material. All right? So, questions about business? Yep. I will look at Wiley Plus when I go to assign grades. Wiley Plus is not a big deal. I've had quite a few emails freaking out about it. Like, you've done whatever you've done at this point, okay? So the point of all that is to get you working problems. If you don't believe it by now, working problems is really the only way to get better at this. If you haven't worked many problems either on Wiley Plus or the stuff I've assigned to you, it's pretty late in the day to be doing that. But once again, for exam 3, the best preparation for that is working problems, either Wiley Plus, the textbook, old exams, assignments I send out. You've got to work problems, all right? Reading the textbook, recopying your notes, that sort of stuff doesn't really do much. It's not nothing, but it's not going to, I'm not going to ask you questions like, what did I say on April 22nd? I'm going to ask you to work a problem. All right. So given that, there's a reaction. Tell me what happens. Give you a couple of minutes. No problem. $60 more seconds. All right. So do you have a leaving group? Everybody's saying yes. What is the leaving group? All right. So I've said this, but I haven't given an example yet. What's the hybridization of the carbon the bromine's on? It's sp2, so it can't do any of this stuff. All right, there is no E2, E1, SN1, SN2 on an sp2 or an sp carbon. For an sp, if you think about it from an SN2 perspective, right, backside attack, the nucleophile would have to plow through the middle of this ring. Can't do that. E2, you might think, well, what couldn't we do an E2? And in fact, you can sort of do an E2. So I don't want to tell you you can't, that's not a leaving group. Bromine's a leaving group. And there are chemical reactions where that bromine leaves. So you're going to cover this, well, depending who you have. I'm not going to give away names. But one of the people teaching 223 in the fall doesn't do a whole lot of aromatic chemistry. That colleague and I spar on this quite a bit. But this would be aromatic chemistry. There are reactions where you could make this bromide leave, either by substitution or elimination, but the substitution is not an SN2 or an SN1, and the elimination is not an E2. Okay, so the other thing then is this bromide can't just spontaneously leave. That would give an sp cation. Sp cations, right? Like the whole thing about an alkyne anion being more stable because the electrons in an sp orbital are more stable than electrons in an sp2 or sp3. You get the reverse for a cation. So an sp cation is really unstable. All right, so that bromide, the upshot is for chapter 7, if you see a bromine or a chlorine or an iodine on an sp2 carbon, it's not going to do any chemistry for chapter 7. Next semester, it'll do some chemistry on some sp2 carbons, but not ever SN2, SN1, E1, E2. All right, so if the bromine's not a leaving group, now do we have a leaving group? Anyone? All right, we do not. Some people, occasionally people will look at this and be like, oh, what about the hydroxide? Or I keep calling it a hydroxide. What about the alcohol? All right. OH hydroxide is never a leaving group in chapter 7 reactions either. It's way too strong a base. So the leaving groups in chapter 7 are going to be weak bases. Chloride, bromide, iodide, sulfonate esters. Now, you could protonate the OH and make it leave. Okay, but that's going to be incompatible with a strong nucleophile or a good base. All right, if I've got a good nucleophile around, I can't have an acid strong enough to protonate the OH. So what happens here? It's hard. Students never want to say this. Nothing. Bupkis, zip. You mix your chemicals up, you go away, you come back all excited, and nothing's happened. All right, the actual way we normally would say this, no reaction. Let's say, though, I want to make Let's say that compound is very important to me. I really want to make that compound. So what do I have to do? So so you could put this reaction in acid. That's what I was going to say. There's basically 3 ways. There are 3 ways to turn an OH into a leaving group. Strong acid. All right, so you're going to turn your OH into an OH2 plus. Okay, that's one way. And then there are two ways you guys don't know yet. There's a reagent called SOCl2 that turns an OH into a chloride. Yeah, no, that's it. I don't know why I'm putting one there. Hang on. All right, so you've seen sulfonate esters, OTS, OMS. Those are good leaving groups. You can make them from TS chloride, MS chloride. So like I said, the strong acid approach is pretty hard to do. So if we look at this, right, sodium thioethoxide, this is not a strong base. It's a really good nucleophile, and S minus is a really good nucleophile. Right, so if I put here sulfuric acid, and sodium ethane thioethoxide, this is just going to give me sodium bisulfite, and I'll protonate my sulfur. And not much happens. You could put enough acid in there that you protonate the OH, and then maybe the neutral sulfur attacks. But you're going to protonate a bunch of other stuff. You're going to have to use a lot of strong acid. So that's not a, again, at this point in your development, that's a pretty good approach. But generally speaking, you don't ever want to mix strong acid let me get it written down. All right, so generally speaking, you don't ever want to mix a strong acid with a strong base as reagents, right? Because they're going to react with each other. So if I mix a strong acid with a strong base, they're going to react, and I'm going to end up with their conjugate acids and bases, which are weak and aren't going to drive my reaction. So like I said, right now, but coming into today, if I had given you this problem, telling me to add an acid, that would have been the answer. But the better approach here, I'll just come over here. It's always a pain when I draw one of these big molecules. All right, the better approach here by a fair amount is going to be one of the bottom two. And actually those bottom two in this case are equivalent. So it might look something like this. Right, so I would say, and again, when you see the, I don't think I've done this a lot, when you see a reaction arrow that's got numbers in it, right, 1, 2, what I'm saying is first we do this, whatever it is. So here, first we treat with thionyl chloride, and then we're going to actually get the product of that reaction. All right, we're not just dumping it. We might. Sometimes maybe 1, 2, 3, 4 means we just dump it all in the same flask. Usually it means we do this first thing, we isolate the product. So you guys have been through around the lab now. First, we do thionyl chloride, we work the reaction up, we do an extraction, we dry it, we rotovap it, there's our product. And then we do the second thing. And if there was a third and a fourth, we'd keep doing that. Right? You might purify it in between. This is really just shorthand, so I don't have to write out, 100 structures. All right. You could also have tosyl chloride and triethylamine. Tosyl chloride and triethylamine will turn that OH into an O-tosylate, OTS. The SOCl2 will turn that OH into a chloride. And then it's a leaving group. And then, the original conditions I had here, I have a good nucleophile. It's a primary leaving group, polar aprotic solvent. SN2 is going to be really nice there. Because this is a really common problem. Alcohol functional groups are really common. They're easy to make. You'll see some chemistry in Orgo 2 where you can make alcohols from a whole variety of things. If you want to turn an OH into a leaving group, you've got to do something to it. You can't, if I treat, sodium thioethoxide is not a super strong base. It's a good nucleophile. But if this was a strong base, it would just take that proton off. An OH is a weak acid. So if my reagent, if my nucleophile is a super strong base, it's just going to take the proton. Acid-base can always happen. In fact, all the reactions you learn can always happen. The molecules don't know what chapter you're in. They don't know what you want. They don't know what I'm trying to ask. If I actually mix chemicals together, they just do whatever nature directs them to do. Strong acid and strong base go together. It doesn't matter if you got a leaving group. Strong acid's going to react with the strong base before anything else can happen. Yeah.
Wouldn't 2 and 3 create like HCl? And then would that ever react with the...
So that's actually what the base here is for toluene. Let me go ahead and I'll put that up. I'm not going to go into the mechanism for the SOCl2. It does. It generates HCl gas. Generates SO2 gas and HCl gas, and that blows out the top of your stack. And so again, like I said, all these reactions all happen. So this is now a little bit more complicated a molecule than you guys have seen. So generating HCl might not be the greatest idea in the world. Certainly generating actually SO2 is not a problem for reacting with the rest of your molecule. It's just a really noxious gas. And so we used to do this we did this reaction once in Old Salem before the renovation, and the hoods were no good. And sometimes they would just go down. You wouldn't know it. It still sounded like they were on, but it turned out they weren't really evacuating the lab. So we start this reaction, we're generating SO2, and within 5 minutes we'd cleared the building. So that's fun. We have not cleared Salem yet. We have not had to evacuate Salem. Some of that is it's new, and some of that is about half now of New Salem's existence has been COVID times. So anyway, we have that to look forward to. At some point, it's a chemistry building. At some point, we will have to evacuate. So yeah, SOCl2 is going to generate SO2 and HCl. Both of those are gases. You do this and you reflux that, and both of them just blow out the top of your reaction. Toluene sulfonyl chloride, the reaction is, I'm not going to ask you guys this mechanism, but I'll put it up. And like I said, I'm going to use triethylamine. Triethylamine is a nice, strong base to soak up HCl, or strong acid. The way this works, the alcohol, the oxygen attacks the sulfur. You displace the chloride, and then triethylamine takes that hydrogen and gives us the tosylate. So this is what our OTS looks like. And then triethylammonium chloride is not a very strong acid, right? Triethylamine is a strong base, so the conjugate acid is not a very strong acid. And if you look at that then, if the OH is on a chiral atom, we haven't done anything to that chiral atom, so you keep the same stereochemistry. This is coming in late in the game, so I can't imagine I'll ask you this, but I suppose you're Orgo 2, not that you're going to, right? Most of you are going to take Orgo 2 next fall, which is a ways off, right? A few months away. So you're probably not going to remember this, but I'll put this up anyway. So if we use toluene, if we make a tosylate, I don't know what I'm doing here. Okay, so if I take a chiral alcohol and I treat it with toluene sulfonyl chloride and a base, I don't touch the chiral atom. I never do any chemistry on that chiral atom. So if the OH is out, the tosylate winds up out. It turns out that thionyl chloride, so the oxygen again attacks the sulfur, and then the chloride minus comes in and kicks out the sulfur, and so you get an inversion. Which means, right, if you use thionyl chloride, if this had been a chiral atom, right, the SOCl2 inverts the stereochemistry, and then you do an SN2 that re-inverts it. So you wind up with the same configuration. So really, which one of those two you want? Like I said, in this example, this is not a chiral atom, so it doesn't matter. I can use either 2 or 3 here, and I get a leaving group. If this alcohol was chiral, it would matter, right? If I wanted to retain my stereochemistry, I would need to use SOCl2. I would do an inversion to the chloride. I'd do an SN2 inversion back to the original. If I wanted to invert it, I would use toluene sulfonyl chloride. I would make the leaving group, then I would invert it. Like I said, that's a lot of detail. I'm not going to. At this point, just what I want you to know is these are the 3 ways to turn an OH into a leaving group. Questions about this one? So the take home from this problem is leaving groups on sp2 carbons, alkenes, aromatic rings, don't do any chemistry. Don't do any chapter 7 chemistry. They definitely do chemistry. And then if you need to turn an OH into a leaving group, you can't just kick out OH. All right, hydroxide doesn't leave in SN1, SN2, E1, or E2. So you've got to turn the OH into a leaving group. You can protonate it, turn it into a water. But again, a protonated alcohol is going to be a strong acid. So if I end up with something that looks like this, all right, so if I protonate an alcohol, I get a water. Water is a good leaving group. But now, if I have a nucleophile that's a strong nucleophile, it's got to be at least weakly basic. Instead of doing an SN2, I'm just going to do that, right? That nucleophile is just going to take the proton. And then I'm back to having an alcohol. Yep.
So what chapter is this going to be on the exam?
This is all on the exam, and it's all in chapter 7. Yeah. So, and it will show up on the final project a little bit. So if you need OH to be a leaving group, a much better way to do that is 2 and 3 here, SOCl2 or toluene sulfonyl chloride. All right. Questions on that? I can go to the next. I'm going to put something up I've had a lot of questions on. Like I said, the key is up for the substitution elimination problem set. If you weren't at the office hour last night, I recorded it. Probably did about half the problems in that. So if you look at the key and you're not clear on some of those, you've got some video recording of what happened. So. So give me a product for that reaction. I should have drawn a halide on the ring just to re-emphasize that. So you've got 2 leaving groups, right? You've got a bromide and a chloride. They're both on sp3 carbons, so you can do substitution. They've got beta hydrogen, so you can do elimination. If we only had one equivalent of base, which one reacts fastest, do you think? The bromide, right? Bromide's a better leaving group than chloride. You do have a bit of an issue here. You can make a tri-substituted alkene. That's going to be more, all else being equal, tri-substituted alkenes are more stable than di-substituted alkenes. But this di-substituted alkene is going to be conjugated to the benzene ring. So this is going to be a good, benzylic halides tend to do substitution and elimination really fast. However, when I say it would be faster, I think the bromide here would react faster than the chloride. That does not mean all the bromide would react and then the chloride would react. If I use one equivalent of base, probably I'm going to get a mixture. I'm going to have a lot of bromide react, but I'm going to have a little bit of chloride react, and I'm going to have some molecules where they both react, and that will suck up base, and that'll mean I also have some starting material that doesn't react. All right, so it would be a mess. Anytime you have a couple of reactive sites on a molecule, if they're not super different in rate, and this is something that for you guys at this point is would be really hard to judge. But if they're not super different in rate, like this one reacts immediately and this one takes a week. If you don't have that kind of difference, then probably they're both going to react. So the best thing to do here is just make them both react. If you drive both reactions to completion, both functional groups to completion, you get one product, or you get fewer products, right? All right. So what sort do we have a strong base or a good nucleophile? Yeah, we get, so right, cesium is going to be +1. That makes the OCH3 minus. So methoxide is a strong base. Localized O negative is going to be a strong base. It's relatively small. A relatively small strong base is going to be a good nucleophile. So it can do both SN2 and E2. What are we going to do here? I'm going to do E2. I've given you the temperature. Strong base at high temperature is going to do E2 if it's possible. So let's think about E2. Let's think about the bromide first. There's actually 2 protons here. There are 2 beta protons for that bromide. So it turns out, if I take one of those protons, I will get the trans-alkene. If I take the other proton, I will get the cis-alkene. All right, so remember, I don't even know where I want to put it. I guess I'll just write it under. So in an E2 elimination, the beta proton that gets grabbed and the leaving group have to be anti-coplanar. All right, because you've got both, and there's free rotation around the sigma bonds, you're probably going to end up with the more stable, well, you get the more stable alkene because it comes from the more stable conformation. Yep.
I know this is kind of an early on thing. Can you remind me how you actually identify where it was the beta one?
Sure, yeah, no, that's, all right, so it all starts with how we define things. And kind of a crappy nomenclature thing we do in chemistry is, like, there's IUPAC rules for naming a molecule. But then there's stuff like this. This is nomenclature, right? Alpha carbon, beta carbon, gamma carbon. And it always depends, and that's not standardized, right? So in chapter 7, talking about an alkyl halide, the alpha carbon is defined as the carbon with the leaving group. All right, so the carbon with the bromide is alpha, carbon with the chloride is alpha. And then you go in order out of that. So any carbon bonded to the alpha carbon is a beta carbon. So you can have up to 3 beta carbons. All right, so that carbon's alpha. That makes this a beta carbon and this a beta carbon. That carbon's alpha, that's a beta carbon, and that is a beta carbon. So for a secondary bromide, there's going to be 2 beta carbons. Secondary chloride, there's going to be 2 beta carbons. You don't have to worry about this one. This beta carbon has no hydrogens. So there's no beta hydrogen on this carbon. This beta carbon has 2. All right? So these are both described as beta hydrogens. And like I said, depending on, we'll go through the Newman projection on the next one. That will be the one that actually matters. those two hydrogens can both be grabbed next. The two hydrogens beta to the bromide can both be grabbed. Right, like I said, if you grab, well, as it's drawn right now, this proton, again, I'm not going to go through it right now, but I will here I'll do it for the chloride. The proton I just circled is anti to the leaving group. So that one, in this conformation, the base is only going to grab that proton. All right, and right now, the arrangement of that bond is such that you're going to get a trans double bond. So the more stable Newman projection generally leads to the most stable alkene. And there's more of the more stable conformation. So the odds are that the base is going to encounter that proton rather than that proton. So let's go ahead and put that, and we said that would go first, so let's just draw this in as a trans double bond. That'll be the major. So that compound will form in there. That's probably the first thing that happens. Right? The bromide's a better leaving group than chloride. Better in this case means it reacts faster. The alkene is conjugated to the benzene ring. That's good for a lot of stability. So now we need to look at we have 3 beta hydrogens next to the chloride. Right now, as it's drawn, the proton to the right, this proton here, is not anti to the leaving group. So in this conformation, that proton cannot be grabbed. On the other side, the proton that's back, that is anti to the chlorine. So in this conformation, that proton could be grabbed. That would give you a di-substituted alkene, which is not quite as stable as the tri-substituted you'd get by abstracting the one next to it. So the tri-substituted is going to be our major product. The base is relatively small, so you don't have any kind of steric hindrance for it to get in and grab the proton. So what we need to do, if we're trying to see about this proton being grabbed, really we have to draw a Newman projection looking at that carbon with the chlorine. We want to draw our Newman projection looking down what's going to become the pi bond. All right, so I'm going to put the front carbon, I'm going to have the front carbon be that one. And if I'm looking at it like this, there's a chlorine sticking out at you guys, so it's up to my right. There's a proton back to the left. And then there's all this mess. So 1, 2, 3, 4, and a benzene. Down. Right, there's the front carbon. Now the back carbon, got an H sticking out at you guys. Methyl down and into the board. And then up is an ethyl group. All right, so that is a Newman projection as the molecule's drawn. I'm going to go ahead and circle the beta hydrogen. All right. That green circled beta hydrogen is the one we're going to try to abstract. And so what we have to do is we have to, and I always phrase it this way and it's incorrect. We don't have to do anything, all right? This molecule is constantly rotating around all the single bonds. All of them. And so what's going to happen is it's adopting all these different conformations. We have in solution, hundreds of conformations of this molecule. The base can only react with this hydrogen when that hydrogen is anti to the leaving group. So the more often you have a proton anti to the leaving group, the faster it's going to react. The more accessible that proton is, the faster it's going to react. The more stable the conformation where the H is anti to the leaving group, the faster it's going to react. All right, so what has to happen for that proton to be anti? If we're thinking about this, we need to rotate, I'm going to rotate the back carbon until this H is up here. So this is an equilibrium. I'm going to draw my front carbon the same. Sorry, not there, the other way. All right, so I'm going to bring this hydrogen over here to where it's anti. That means the methyl has to go up. Ethyl would come over here. And now my beta proton is anti to the leaving group. That is the only conformation of this molecule that can give me a tri-substituted double bond by grabbing that green proton. All right, so that's the HCl that's going to be abstracted. My base. Base is going to come in here. Remember, E2 is one step. The base makes a bond to the beta hydrogen. The CH electrons make a pi bond. The leaving group leaves with its electrons, all simultaneously. Okay, so from there, draw the alkene you get from that elimination.
Is all the Newman stuff going to be for E1 also?
No. We'll talk about that in a second if you want. All right, so the way to work this out, when you have your Newman projection with the beta proton anti to the leaving group, what's going to happen is, right, two things that are, if you draw this line, the beta proton and the leaving group, you've got this line there. Anything that's on the same side of that line in the Newman will end up on the same side in the alkene. So the methyl and the H will be cis. The ethyl and the rest of the molecule will be cis. And then anything that are on opposite sides will end up trans. Okay, so H and the ethyl will be trans. Methyl and the rest of the molecule will be trans. So the product will be there's my alkene. All right, the rest of the molecule I said is going to be trans to the methyl. Yeah, trans to the methyl. And the rest of the molecule is going to be cis to the ethyl. And then I'll put that H on here. Right? The H and the methyl end up cis as well. So that is the only, that alkene, that's the only one of, that's the only diastereomer of the tri-substituted alkene you can get. Yeah. I'm glad you asked that. All right, so you're wondering about wedges and dashes here. It's not because it's E2, it's because it's an alkene. All right? These are sp2 hybridized carbons. They're trigonal planar. All right? If you put a wedge on one of these, if I put a wedge here, then that one has to be wedged. They're cis. They'd have to both be coming out at you. That would then have to be dashed, and that one would be dashed. You'd be looking at the alkene this way. A far better way of drawing an alkene is just with all of them planar bonds. Okay? There is stereochemistry here. Right? This is, well, actually, tell me if this is an E or Z alkene. I'll give you, like, that, yeah. Think about it, work it. I'm going to give you like a minute to try to come up with it. And the point is, it can be E or Z, all right? We could have had the ethyl group be trans to the rest of the molecule, methyl cis to the rest of the molecule. That would be a diastereomer. So there is stereochemistry on that alkene. But you don't draw a wedge or a dash. And I mean, in a class of 44, hundreds of you drew wedges and dashes on the assignment. That's like my main. You guys did a pretty decent job of figuring out what the mechanism type was. You did a less good job about drawing what the product of that. And then even when you got the product, a lot of you did the right, you got the right alkene, but then you just threw wedges and dashes on it in a kind of haphazard way. Generally speaking, you're never going to draw a wedge or a dash on an alkene. All right, E or Z? Who says E? Who says Z? Like 8 to 2. All right, good. So let's go through this priorities. The first thing to do is assign priority to one of the sp2 carbons. All right, so I'm going to start with the left one. I've got H in carbon, so carbon is 1, H is 2. Again, this is like R and S. You assign priority based on atomic weight at the first point of difference. Carbon is heavier than hydrogen. Next one, I'm going to do the one on the right. Carbon versus carbon, that's a tie, so you have to keep going. This carbon is bonded to a C, an H, and an H. This carbon is bonded to an H, an H, and an H. So the CHH is 1. The HHH is 2. All right, if the ones are on the same side, if they're cis to each other, this is a Z alkene. Here, the left alkene, the di-substituted alkene we made first is E. You can also call this one a trans double bond, all right? You've got the protons trans to each other. If you have identical groups that are trans or cis to each other, you can just call the alkene trans or cis. If it's trans, it's going to end up being E. If it's cis, it's going to end up being Z. So this would be an EZ diene. EZ diene. Whew. Question?
So you're assigning the priorities to figure out if you're comparing the two that are on the same carbon.
Yes. Yeah, that's a good way of saying that. Right, so when I'm doing priorities here, I'm looking at two groups that are bonded to each of the carbons. So I take one alkene carbon, and I look at the two groups bonded to it. I'm going to have a 1 and a 2. Then I do the other alkene carbon, and I look at the two groups bonded to it. I'm going to have a 1 and a 2. So there's no 3s and 4s. You're going to end up with 2 1s, 2 2s. If the 2 1s are trans, it's an E. If the 2 1s are cis, it is a Z. You can also use the 2 2s, right? If the 2 1s are cis, the 2 2s have to be cis. If you somehow get the 2 1s being trans and the 2s being cis, take a deep breath, step back. You have done something wrong. All right? Okay. So there was a question about E1. So let's do the same alkene. All right, so same alkene, same bromide and chloride. But now, do you have a strong base? You do not. You have ethanol. All right, ethanol is all you got there. It's a good Friday night. It's a bad E2 reaction. So no strong base. It's going to either be SN1 or E1, as long as you can make a carbocation. Secondary benzylic, that's going to make a really nice carbocation. In this case, the bromide's going to react much faster than the chloride. Bromide's a better leaving group. The cation you get is way better, right, because it's resonance stabilized. So the bromide's going to react super fast. Chloride's going to react pretty slow. But you still can do it. It's going to make a secondary cation. So that's okay. So the question was, do you still have to do all this Newman stuff? And the answer is you do not. In an E1, so we're going to get an E1 here, and we're going to get an E1 here. No strong base, no good nucleophile, so we're not doing SN2 or E2. We can do SN1 or E1, and the temperature is elevated. So E1 is going to be favored. And now the same thing. E1 is always going to give you pretty much all the alkenes in the order of their stability. All right, so the major product is going to be the most stable alkene. So the trans conjugated alkene. Again, let's just stipulate that. Oh, by the way, this bracket, basically what I mean is you put brackets around a molecule that forms like an isolable, stable molecule that forms in the reaction but isn't the final product. Right? This is a completely fine molecule. You could make that a variety of ways. But in this, under the reaction conditions, it doesn't stop here. All right, so now let's do an E1 from there. So draw the first step of the E1 mechanism. Just the first step. Then we'll talk about then we get to your question. All right, first step of the E1 mechanism is the same as the first step of the SN1 mechanism. Leaving group leaves. And we're going to get a carbocation out of that. And sure, chloride if you want. All right, so chloride takes off, takes the electrons with it, leaves a secondary carbocation. Secondary carbocations can do a whole bunch of stuff. They can rearrange. I think everybody who's come to an office hour and talked about a reaction where a rearrangement happens asks if you guys are going to have to predict a rearrangement. And the answer is probably not, but it's not entirely unreasonable, right? If you get a secondary cation, there's a really good chance it's going to undergo a rearrangement. Pretty much any time you draw a carbocation, you should think to yourself, can this rearrange? Right? If something on the carbon next to it can move over and you get a more stable cation, that's probably going to happen. So here you might well predict, oh yeah, this hydrogen can move over and I get a tertiary cation. That'd probably happen. I'm not going to talk about it right now because we don't need that to happen. I'm going to talk about just looking at this hydrogen being pulled off. So we have a carbocation. All right, so it's trigonoplanar, sp2 hybridized, which means it's got this vacant p orbital. So we're into your question now. So on the carbon next to it, we could have an R group, right? This carbon's got an R group, we got a carbon, R group coming this way, and an H going the other way. Sorry, I'm going to have this R group coming forward, and an H going back. It's a secondary halide. And now, this carbon all right, so this is a chiral atom right here. The carbon I've just shown with that CH is a chiral atom. And so again, when that beta hydrogen, so over here in the E2, the beta hydrogen that gets grabbed has to be anti to the leaving group. For the same reasons that in an SN2, the nucleophile has to do a backside attack. There is an orbital requirement for abstraction of the hydrogen from the sp2 carbon, or next to the sp2. But now the orbital, right, we're not looking at an anti-bonding sp3. We've got a vacant p orbital. So the hydrogen has to be lined up with this p orbital to get grabbed. Right, so now the base can grab that H and pump the electrons into the p orbital. And so drawn this way, R and the methyl would end up cis. All right? That make every, let me, what were you going to say?
I was going to say what happens if the chiral carbons are touched together.
There you go. There you go. Excellent. So unlike over here, there's only one way to be anti to the leaving group. And so that means we're only going to get one of the alkenes. Here, though, I'm going to leave the carbocation the same. You can imagine rotating around the CC single bond there. All right, so now the CH bond, the beta proton, still lines up with that p orbital, but that rotates these as well. So now we have we've turned that over, but we can still do what we need to do here. Beta, the base can grab those, the proton, those electrons can get pumped into the p orbital. But now, the R is cis to the ethyl. And so the result is we can get both of those. So let's draw that. This would give we'd get both of those alkenes roughly in a rate. And the other thing is we would also get our base in this case is ethanol. So in both cases we wind up with protonated ethanol and chloride. All right, that's a strong acid. So think back to chapter 8. If I have a strong acid and an alkene, I can protonate the alkene, get a carbocation. All right, so this is going to equilibrate. We're essentially going to have these two alkenes in equilibrium. And so we end up in an E1 elimination. In all E1 eliminations, what we end up with are the most stable alkenes as the major product. If there's a small difference, like in this case, there's really a pretty small difference. In the top one, we have methyl cis to this big group. In the bottom, we have ethyl cis to the big group. Methyl and ethyl are different in sizes. The top one is the more stable one. If you look at the big carbon on the left alkene, if you look at the big group on the left alkene carbon, in the top it's trans to the big group on the other alkene carbon. Let me try to make that a little more clear. All right, so this is big, this is big. Right? The two big things are trans. That's a little more stable than if the two big things are cis. But in this case, the difference between the big group, the difference in size between an ethyl and a methyl is not very much. Right? So the difference in energy between those two is not huge. On the left-hand one, right, the difference in energy between having the H's trans and having these two big groups cis, like a phenyl ring and the rest of the molecule, the difference between having those cis and trans is pretty big. So we're really only going to see the trans there. On that second alkene, the difference is not so big. So you're going to have more of this, but you'll see this one as well. And in an E1, there's no way to get around that you're going to have a mixture of those. In the E2, we only get one. I forget which one we get, right? We only get the less stable one. Good. I can see it in your eyes. You've all got it. Wonderful.
So,
I should show you I'm smiling when I say that.
so a test would just be like, show us the product of that reaction, or just keep the bottom when you don't have to show it.
Yeah, so like I said, I mean, as you look at old exams, like read them carefully. There's like the big reaction page, like the page of just the reaction slog, that almost always says draw the major product, right? The major product is one thing. You know, if you think, like on this one, you might think to yourself, yeah, man, it's E1, these are pretty close, I'll draw them both. Like if it's E1 and you draw them both, that's fine. If it's E2 and you draw them both, like if you had drawn both of those alkenes over there on this problem, again, as I grade those, as I grade problems in this set, in this chapter, right, the first thing is, do you identify the correct mechanism? And like on the homework set, I ask you to explicitly tell me what the mechanism is. And like I said, looking at your, I'm not all the way through them, but so far everybody's writing E2 when it's an E2. Now, sometimes people write an E2 and then don't draw an elimination product. All right, so that's going to be a penalty. Sometimes people will say E2 and they draw an elimination product. That's good, but they don't take into account that it's got to be an anti-coplanar proton and leaving group arrangement. All right, so that's a penalty. In an E2 where you're only going to get one and you like draw them all just to cover your bases, like that's wrong. E2 won't give you all. Covering your bases is not always the way to go. SN2, I guess the other thing I'd say about that, like what I've looked at so far, on the SN2, you have to show stereochemistry. So it's always inversion on the carbon that's attacked. Any other carbon of stereochemistry doesn't change. So quite a few I've seen, not a lot, not all, not most, but quite a few. Like there's a chiral center away from the leaving group. That doesn't change. Chiral center with the leaving group changes. And if you don't show that, again, if you tell me it's an SN2, you draw the SN2 product, but you don't show stereochemistry, that's sort of the last thing I look at. So if it's a 5-point reaction, you tell me it's SN2, good. You draw the right SN2 product, good. You miss the stereochemistry, it's going to be 1 or 2 points. So there's not, you know, it's not all or nothing. Yep. Yeah. Or, so, like there, if it's an E1 or an SN1, you want to cover your bases and just draw like everything you can think of that might plausibly happen. Not a bad idea. If I say the major product, though, and you like draw this, but you don't do this one, like that's wrong. If you draw this one but not that one, when that one's, there's more of that than this, that would be wrong. So if you decide to draw one on an E1, you need to make sure it's the most stable. But again, like I don't want you guys, I want to be rigorous about it. but I don't want you freaking out that like a 5-point reaction is all or nothing. Like you might miss all 5 points. If it is, let's say it's clearly an SN2, and you tell me it's an E1, and then you draw not an E1 product, but it's also not an SN2, or if you don't draw a real product, like you're just going to miss all the points. So I'm not promising to give you some points for everyone, but I'm looking for different things there. One is you can tell me what you think should happen, what mechanism should happen, but then you need to be able to tell me what that mechanism produces. You need to be able to draw all of them, right? You need to be able to draw an SN1, SN2, E1, E2.
You're gonna ask like stereochemistry, like
Oh, I would say. Then the other thing is there are product like that assignment is like a little mini exam. So there's going to be a mechanism question. There might be 2. All right, and in those, very often I'll ask questions about like that's where it'll be like the EE is something weird and maybe it rearranged, and you'll have to explain those things. The reaction page, generally, you just draw me a product or 2 and call it good. Yeah.
So if it says draw the A positive E1 reaction and it's close, you can draw a 3 product?
Or get the one that's more stable. Yeah. Like so if it's not, if you drew this one and that's all you drew, I'd be fine. Right? There's probably a little bit of the cis here too, but I'm not enough. If you only drew the cis there, that would be a problem. I mean, so with 2 alkenes, we can figure this out, right? How many possible stereoisomers are there for this alkene? 4, right? Go back to, this is studying for the final now. The number of possible stereoisomers is 2 raised to the power of n plus m. N is the number of chiral centers, m is the number of isomerizable double bonds. This can be E or Z, that can be E or Z. EE, EZ, ZE, ZZ, right? So 4. Complicating matters a little bit, and I haven't really talked about it. You could get an alkene here too. In the E1, you're going to have the tri-substituted alkene is a lot more stable than the di. So you're not going to see the di substituted in E1. In the E2, again, the major product is going to be that. But you'd probably have a little bit of E2 elimination there as well. 5 minutes for some questions. Because you're going to end up with the same alkene. So it probably would happen, and like if I asked for the mechanism and you drew it, that'd be fine. And the same thing applies. What I wanted to illustrate is because you go through a carbocation, that proton has to line up with the p orbital. But there's 2 lobes of that p orbital, so it can line up either way. And that would be true. If you didn't hear it, his question was, why didn't I show the rearrangement? Right? So from this secondary cation, the beta proton can actually slide over. And in solution, it probably slides over and you get the tertiary cation some, and then it probably just gets abstracted some. You can't really tell because the alkene you're going to get is the same both ways.
I actually had like a question earlier. Is that drinkable alcohol? It says methyl alcohol.
No. And it's empty, so maybe it was. 70% ethyl alcohol. It's a nice rum. No, I think I've talked to some people I've talked about in lab with this. The alcohol we buy as a chemistry department is not drinkable. So don't pilfer an ethanol bottle from us. As I always tell students, and I don't know, I assume this is true in COVID times, all right? But, so the drinking age in the United States is 21. You're a deeply, hugely immoral person if you drink underage. Can you see my smile? That was not true back in my day. No. It is, to me, unfathomable that the drinking age is not 18. But it's not. And so as a responsible adult, paid handsomely by Wake Forest, I'm telling you not to drink. Now, what I will tell you is I am quite confident that if you choose to drink, you can find alcohol that is not toxic on campus if you absolutely have to. The alcohol we have is treated in such a way that it's not drinkable. And the reason for that is it's interesting policy. Alcohol is taxed. Alcohol is really cheap to produce. Ethanol is really cheap to produce. And so the reason booze costs as much as it does is it's taxed by the government. We can't afford to pay those taxes, and so we treat it in such a way that you can't drink it. Now, that was not true in 1990, and I can tell you that because I'm still alive. So sorry, Oklahoma State. Yeah, they were just like vast flammable storage for ethanol, and it was pretty easy to slip in there and take stuff out. So it was a different time. We also drove around in reverse. And all right, I think I've got a serious question here. If you want to hang on for a second, yeah. I will probably be available Monday night. I am not available again until Monday, so I will try to get something scheduled Monday night. Yeah, hang on one second. So, to that end, again, look out for an email about where, or look on that class assignment page, or who's supposed to go where. And that will also be true. I am going to ask you, I realize I had told you at one point that you're not going to have to tell me if you don't want to take the final. I am going to ask you to tell me. And the reason is, if there's 30 or fewer people who take the final, I can fit all of you into the same room. All right, that's no pressure either way, but if there are more than 30 of you, some of you are going to have to be up in the lab. So I'd like to just get that straightened out. I will have your grades to you by the end of day Thursday. I'm hoping to have your grades to you by class time on Thursday. Thursday, again, I can't fit everyone in the room. Thursday will be a review, all right? So there's no new material after that. I'll answer some questions about the exam. What I would recommend, and I wish this were another way, as soon as you finish the exam on Tuesday, I would go back and start reviewing exam 1 material, okay? So exam 1 material is oldest. It's going to be the least fresh in your mind. Exam 3 material, I would look at your exam and see what you missed and try to shore that up. Trust that if you knew it on Tuesday, May 4th, you're going to know it on Tuesday, May 8th, all right? The final is not designed in such a way that I expect you to completely re-study the semester. I designed the final sort of like, what do I want you to take away, okay? So study exam 1 stuff most, study exam 2 stuff a little bit, and have some faith. I always go over. I always think that last little comment's not going to take me over. All right, see you all later. Have a good weekend. Yep. Hey. You found that in the bathroom?
It doesn't, yeah.
And there's no, because it was here. So what happened is somebody took that from there. There was one. It's been laying up here with one bud. And evidently somebody took the bud and